Today's lecture is called JAX. Can it beat PyTorch and TensorFlow? What is it all about? We probably all know that nowadays there are two main deep learning frameworks, PyTorch and TensorFlow, but it was not always like this. Historically, there have been other frameworks which are either dead by now or never really succeeded. And of course, there is no reason to believe that this duopoly of PyTorch and TensorFlow is going to persist in the future for all times until the end of our universe. It's quite possible that in the future new frameworks will appear and compete successfully with those two. And of course, even nowadays, many people and companies are trying to create their new deep learning frameworks. Do you all hear me? Do you see the presentation?
Yes.
Okay, good. Then I continue. And today I'm going to tell you about Google JAX, one of the new frameworks which is trying to compete with the main two nowadays. Why did they create JAX? I don't really know. Ask Google people, but probably the AI folk at Google got tired of TensorFlow and wanted a new toy, so they created JAX. JAX is not one library nowadays. There's a whole JAX ecosystem. JAX itself is lower level API. Think PyTorch without NN or TensorFlow without keras. And there is also higher level layer API, FLAX, and another one called Haiku. Why two? Because you might know Google is a big corporation and there is a thing called DeepMind, which is formally part of Google, but in real life they don't want to have anything to do with the rest of Google and always do things differently. So of course, if the Google created FLAX for JAX, DeepMind had to create their own framework instead. So they created Haiku, which is similar to Sonnet, a TensorFlow library, which is used by DeepMind and nobody knows outside of DeepMind. But in DeepMind, they used this library Sonnet instead of keras. And they did the same with JAX, created their own library Haiku, inspired by Sonnet. And there is also OPTAX, which contains optimizers and loss function for JAX, and many other libraries based on JAX. So you can see the JAX ecosystem article. Note that currently there is no dataset or data loaders for classes for JAX. People have to create their own or most often use TensorFlow or PyTorch for loading standard datasets. Let's start with the JAX, which is a lower level API. What is JAX really? It's a Python library which didn't appear out of the thin air. It had its own predecessors. OPTAX was a Python library which implemented NumPy-like functions, but with differentiations, like backpropagation style. And completely different project is Google XLA, or Accelerated Linear Algebra. It's a fast matrix operations for CPU, GPU, and TPU. The same code runs on different devices. It compiles stuff into efficient machine code. It was optional in TensorFlow. For JAX, it's no longer optional. JAX is an AutoGrad-like library based entirely on XLA, and it includes FLAX, a Python API for XLA, which is really low level, and also which is slightly higher level. You can think of JAX as of NumPy with backprop, JIT just-in-time compilation, and GPU and TPU support. There is a link to GitHub, documentation, lecture at AI Epiphany, and this actually first lecture. There are 4 lectures there. You can look at all the stuff. And of course, today I'll give very brief overview of JAX and tell you just the main idea, as you are not going to learn how to use JAX from this lecture alone. You have to do tutorials, official tutorials, or other lectures if you really want to learn JAX. I'll just give a very brief overview of what this monster is. So let's continue. In JAX, you write code similar to NumPy, but using J and P instead of NP. But JAX is entirely based on the functional programming paradigm, and because of that, all tensors are immutable. More on that later. You can calculate gradients with function grad. You can compile Python code to XLA with function JIT. You can add batch dimension to a function using vmap and pmap. And basically, I covered the main functions of low-level JAX. Same code can run on CPU, NVIDIA GPU, or TPU. But GPU version requires strict CUDA and cuDNN versions, much like TensorFlow. So you probably want to use Docker. And there is, unlike for TensorFlow, there is no official Docker images. So you have to create them yourself or find some unofficial ones, unfortunately. Next, JAX uses functional programming paradigm. But what is functional programming? Very brief reminder. In mathematics, there was a thing called mathematical functions. In programming functions were largely based on mathematical functions, but not really, because in programming functions, you could put print, you can put global variables, and so on, so-called side effects. And functional programming means using only pure function. Pure function means it has no side effect. In particular, it receives input data only through the arguments x, y, z. It outputs result only through the return value and nothing else. It does not modify arguments in any way. It doesn't access any global variables. It doesn't have any other side effects like printing or writing files or accessing website, anything like that. That's called pure function, which behaves much like mathematical functions. And this paradigm is very popular among, I don't know, academia, theorists of programming languages, and maybe not so popular in real software development. But anyway, JAX try to follow this paradigm. And what about objects and classes? Originally, in pure functional programming, there were supposed to be no objects and classes. But of course, in Python, you cannot do things like arrays without classes. So with JAX compromises, it allows objects like array or even like neural networks as long as they're immutable. But for example, they can contain some parameters like size of the array or something, but they should be immutable. How do you work with immutable tensors? In NumPy, you can modify arrays like that. You create an array and then you modify 2 elements of the array. In JAX, you cannot do like that because arrays are strictly immutable. But what you can do add and set operation, which works the same way, except that it copies the data and creates a new object, which is now assigned to A. This should be remembered when writing the code. And what does functional programming means for deep learning? In deep learning, you typically have a model which has model architecture and also model parameters like weights, like numerical parameters of each layer. And of course, these model parameters are mutable. So in our paradigm, the model parameters must be separated from the model definition or model code. Like in PyTorch, you have model class, which had model definition and model parameters and everything. Here you cannot have like this. You have to separate model definition and model parameters. In a few slides, you will see how it works in practice. Also, if you are using param, you will have also state, which is similar to parameters, but variables which are not optimized, like averages from batch norm operation, like moving averages. And they're typically called state, and they're like parameters, but not optimized by the optimizer. You cannot have model class like in PyTorch, I already told you, and exactly the same goes, for example, for optimizer. You have to separate code from parameters and even random number generator. A question, is there a connection? Are you still hearing me?
Yes.
Very good. Let us continue, because internet could be sometimes unstable here. Next function is JIT. Make a Python function run much faster. Basically, it's like this. You define a function, Python function, and as you might know, Python language is a bit slow compared to real programming languages like C or C++ or Fortran. But here you can use JIT function, process my function to create a new fast function, which is supposed to be fast. So you think, wow, magically you can make any Python function run faster, much faster, sometimes 10 times or more faster. Magic. But unfortunately, it doesn't really work like that. To some extent, yes, but there are limitations. What does it do? It compiles Python code to the Google XLA code, which, as we know, can run on different devices. It uses tracing, similar to PyTorch trace. But there are limitations. First, the function must be pure. Any side effects, prints using globals are not reproduced. Second, things like the code of the function is very limited. If and for constructions are not supported unless they rely on only static arguments which are known at the time of compiling the functions. It's possible to declare some of the arguments static. The actual compiling happens not when you call JIT, but when you call fast function for the first time. So it only makes sense if you run the same function many times. Moreover, the compilation requires exactly known types and shapes in case of arrays of the input arguments. If the types or shapes of input arguments change, or static values of static arguments change, then the function is automatically recompiled, which can take pretty long time. So this JIT can make the function run faster, but it only makes sense if you run the same code many times and exactly with the same size and shape and types of input arguments. Otherwise, it will be slower because of recompiling every time. Let's move. Then next function, grad. Grad is a gradient of scalar function. I mean, in our company, you probably all know about deep learning and things like backpropagation, and jax.grad just implements backprop for Python code using GNP, JAX version of NumPy. Example is like this. There is a function of sum of the vector components squared. You take gradient and it writes you the gradient. Gradient also uses tracing, but tracing under different conditions. So now things like if and for are allowed. Basically, it's a backprop through Python code. You can also call function value and grad, which returns the tuple of function itself and this gradient. There are even more complicated things like Jacobian. Look at the documentation. By default, grad differentiates with respect to the first argument of a function. Typically in deep learning, you have a model and you always want to know the gradient of the model with respect to model parameters, which we have to optimize. We'll see in a slide or two. Next function is vmap. It's not always needed, but sometimes it's useful to vectorize a function along the batch dimension. For example, here we have a function f(x) which declares some matrix 3 by 3 and multiplies w times argument x. It works only in shape 3. Suppose if we want to batch dimension instead of shape 3, shape 2, 3. This function wouldn't work. But if you apply operation vmap to the function, then it now supports the batch dimension, and it can be executed on data like this. Sometimes it's useful if you have some non-standard, highly experimental neural network layers, but and you don't want to bother with batch dimension. You can write a version with batch 1 and then h batch dimension later. Similar function is pmap. It's like vmap, but works on multiple devices, GPUs, different GPUs, or several TPU cores, not GPU cores. Several GPUs or several TPU cores. Limitation is like this: number of devices must be greater or equal to batch dimension. You cannot have batch larger than number of devices if you use pmap. By default, you cannot run it on multiple CPU cores. Of course, you want to try it without any TPUs, so you want multiple CPU cores. By default, there is only one CPU core used by XLA, but if you specify XLA FLAX environment variable, you can make XLA run on 8 cores. Then you can try pmap on a CPU. There is also very rudimentary communication between devices like psum, and so pmax. Look at the documentation. Do you still hear me? Okay.
Yes.
Okay, good. The next topic is jax pytrees. What is a pytree? Jax pytree is a nested structure of collections like dict, the list, and so on. The end nodes, called the leaves, are typically but not always jax arrays. And also custom collections can be registered for pytrees, like frozen dict and FLAX, for example. The immutable version of dictionary. Why does jax use pytrees? Pytrees typically contain parameters or states of a neural network, optimizer, and so on. As I told you, model code is separated from parameters, and you need some data structure for parameters, and it's typically pytree, basically nested dictionaries, because nested because our network can contain many layers. Each layer has its own parameters, thus nested dictionaries. And jax has special functions to work on pytrees. For example, tree map applies a function to each leaf of the pytree and returns pytree of exactly the same structure, but with function applied to each leaf. And you can also combine two trees of the same structure and size with tree multi-map. Common jax.grad functions support pytree. So basically, if the first argument of a function is a pytree, network parameters, jax.grad differentiates with respect to this pytree parameters and return pytree of the same shape with the same dictionary keys. Next topic, random numbers. Python packages like NumPy and PyTorch, they have a global random number generator with a global state. Global is not very nice, and especially it's not acceptable for functional programming paradigm. In jax, you cannot have globals and cannot even have mutable objects like random number generator in C++, for example, can be not global, but it's a mutable object. You need to separate the random generation code and the state. You need an explicit random generator state, which is called key in jax. You can generate a key from the seed. Then you can use the key to generate random numbers. Okay, but then, for example, I do it again and I get exactly the same result. Why? Of course, this normal is not really normal. It depends on the key. And if you supply the same key twice, you will get obviously the same result. It's not good random number generation. So what do you do? What do you do is to use function split. every time you use a random number generation, you generate a new key. For example, you have key, then you split key 1 from key and the new key. Then key 1 is used only once and key is updated. Next time you can again do split and generate key 2 and update key. So typically you have one key, where variable key, which is updated all the time, and every time you need a new random number operation, you can split key 1 from that and use key 1 only once. That's how random number generation works in functional programming paradigm, where you have to separate random state with a random code. And you can also split 2 keys if you specify 3 keys, or you can split a list of 10 keys if you want. All this possible. Now I'm almost finished with PyTorch. Let's see a minimal neural network example in PyTorch. Let's generate some linear data plus noise. This is a linear function with some noise, and we generate 101 point using the random number generation as I explained. Then we do a linear model with 2 parameters, which tries to interpolate this data with linear function. This is our model. Then we define a loss function as MSE loss. So your typical loss function gets parameters x and y. You call model with parameters and x. Know that how you call model, you have to specify parameters explicitly. You calculate prediction and you calculate loss between ground truth and prediction. Then you calculate value and gradient of this function, and also it goes through JIT for speed and value and gradient. And gradient are taken with respect to parameters. Here it's only list of 2 numbers, but in general it could be pytree. I define the 2 parameters, learning rate, and then training loop. For 100 iterations, I calculate gradients depending on parameters x and y. And then I add gradients to parameters. How I add gradients to parameters? Here I use tree multi-map, which combines 2 pytrees. One pytree params, the other pytree grad, and the function is p minus learning rate times gradient. So we implemented the simplest form of SGD, or here it's rather gradient descent, not SGD, because you don't have batches. And that thing works. In real life, you use optimizers from OPTAX instead of simple SGD. Next chapter, don't worry, it's going to be very short compared to chapter 1. Only one slide about OPTAX. Let's change our code to add OPTAX. We declare our optimizer OPTAX add, specifying learning rate. But you already know that optimizer cannot be an object with a state. So state should exist somehow separately. And that's how you do it. You initialize optimizer called init, specifying params, parameters of neural networks. And based on parameters, it's create an optimizer state. And then at each iteration, you update optimizer state. You call optimizer updates, applying gradients, and all optimizer state. And the result is updated optimizer state and gradient updates. That's how functional programming works. And then you call OPTAX apply updates to parameters. Basically, it just numerically adds update pytree to parameters pytree. And here is the same example, but I use Adam to optimize. Also, OPTAX contains the various loss functions, schedulers, and so on. You can read yourself. The next chapter 3 is FLAX. Do we still have connection, people? Can you hear me?
Yes.
Yes, we have.
Very
Yes, we
good.
do.
Very good. What is FLAX? Flexible JAX is a layer API for JAX. Sync is something like tf.keras or torch.nn. And as we remember, it's used by the whole Google except for DeepMind, which has the different frameworks. And actually, there was old FLAX, FLAX.nn, which was deprecated and eventually removed. Nowadays, there is a new FLAX with API FLAX line, which is usually imported as an N, but it's not exactly the same as the old NN. So forget the old FLAX. I'm going to tell you about the new FLAX. Let's create a model of the linear layer and then dense phi output features 3. But of course, it's functional programming, so we know that this model is not complete. It's only model code, but it should also have model parameters somewhere. How to get model parameters? To get model parameters, you call the init function, and the init function gets a random generator key, which is used only once, key init, and also sample input. X is a sample input so that the init function knows the model input size and shape. And then it initializes the model. Basically, it's again some sort of tracing through the Python code and create model parameters, a frozen dict. For this simple model, the frozen dict has a simple single key param, so I'll explain soon why. The parameters are always under the key params, and here you only have one layer with bias and kernel. Kernel, it's actually a bad name, but it's actually W of the linear layer. And here is a typical use of jax.vmap. Lambda p shape, it creates the pytree with the shape of each leaf instead of the leaf itself. This trick is standardly used in JAX to print the size of the parameters. So once again, first you have model code, but to get model parameters, which are separate because of functional programming, you call init function. Remember, for OptAX, there you had also init. It's a standard pattern used everywhere in JAX universe. How do you run the model? Again, you cannot just call the model object like in PyTorch. You have to call apply function and supply parameters, explicitly supply model parameters and also argument x. Or if your model have randomness, for example, if you have dropout layers, you have to specify random number keys for every layer which have randomness. It's a bit inconvenient, I would say. Also, you can have, what about more complicated models than one layers? You can use sequential models, or you can create your own model class. Model class is inherited from NN module, which is a Python data class. If you don't know what is Python data class, learn it, it's interesting. You declare the fields with a type in the beginning of class, and it automatically creates constructor to initialize all these fields. And because constructor is already busy in data class, setup happens with a setup method, which is called not when object is created, but when init is called. And here we declare two dense layer, and finally the call method is actually used to run the neural networks. You apply first layer, then ReLU, then second layer. And you create this class with two arguments, fit1 and fit2. That's how you create a custom model in FLAX. Or there is a simpler way which works in many cases. Without setup method, you can just use call method and wrap it in compact decorator. There, because of compact decorator, you can declare layers inside of the call method. Anyway, they're correctly registered and correctly added to the dictionary of parameters because of magic of compact decorator. Here I declare the layers and immediately call them in call method. That's how people usually write models in FLAX. The convolutional model is not much more complicated. You put convolutional layers and ReLU and average pool. Notice how con with an object which is created and registered, it has parameter and then called. But ReLU and average pool are just functions. No objects, no parameters, no registration, and compact as you always. Can we write a custom linear layer in FLAX? Yes, you can. Again, you need compact for some FLAX magic, and you declare parameters just in call function. I guess if you didn't use compact, you had to declare them in setup. This is a custom linear layer. You have to declare initializer, switch, reasonable default, and you declare parameters with self-para method, parameter name, initializer, and shape. And again, because of compact magic, is not recreated every time you call. It's created once, registered on initialization, and then this parameter from the dictionary supplied is used when you run neural network inference. That's the code for custom linear layer, which is similar to predefined linear layer. Next is a problem of state. As I told you already, what if we have a model with state or non-parameter variables? For example, which batch norm has such state? Variables which are not parameters, which are not optimized by the optimizer. How do we do it in FLAX? It's a bit complicated, a bit inconvenient in FLAX. First, you have to initialize, run model init. It initializes all variables, parameters and not parameters. You remember that parameters had dictionary key params, and other variables which are not parameters, the state are using different keys. And then you have to separate state into state and parameters. It's important that only parameters must be optimized and not state. After you separate, you supply parameters to the optimizer, but not state. At inference time, you have to recombine in parameters and state again into a single dictionary like that. And you supply this full variables, parameters, and state to apply. Moreover, you have to specify the keys, everything except parameters which are mutable. And the mutable keys are changed in the model and returned into the as a new updated state. So state is updated in this line. For example, batch norm state is updated at every inference, while parameters are updated by optimizer steps. That's how it works. Not very convenient, but that's how you do it in FLAX. Actually, FLAX has a higher level abstraction called train state, which combines model, parameters, and OPTAX optimizer together. I don't want to overload you with information. If you are interested, you can learn from the tutorial how to use train state. And finally, the final chapter today, well, almost final chapter of today's lecture is Haiku. This Google DeepMind alternative to FLAX. Let's look at it. In FLAX, it's even more, Haiku, is even more functional programming style than FLAX. Here in FLAX, you always have to define neural network module as a class. Here, module doesn't matter. There is something called module, but it's not very important. What you must specify, a function. For example, for linear layer, you specify a function like this. Neural network is a function, but then you cannot use this function directly. You must first transform it, otherwise Haiku models wouldn't work. You run Haiku transform function on this forward and create a model function. And then it's similar to FLAX. You run init on this model object. Now some kind of object is created, but you don't create this class explicitly. You initialize them all. They'll supply in random number keys and sample input, and then you apply the model. Note that by default Haiku always needs a single key, and then it automatically applies it to generate splits new keys and gives each to each dropout layer. For example, if you have dropout layers, and compare FLAX and Haiku. In Haiku, all magic happens in Haiku transform, while FLAX has a module class with some magic and especially compact function. So basically what happens here in transform function in FLAX happens in module and compact function. There are different versions of HK transform. If you want to use apply without random key, if you don't have any dropouts in your model, you can do additional transformation without apply RNG. So now you call apply without random number key. If you have a state, what do? You actually do transform with state. And now init generates parameters and state. You see, Haiku automatically separates parameters and state. You don't have to do it by hand like in FLAX. And apply takes parameters and state. You don't have to combine them by height. So in my opinion, and of course, only parameters are sent to the optimizer. So, in my opinion, if state is involved, parameters plus state are managed cleaner in Haiku than in FLAX. You can have modules if you want, but in Haiku, it's only a lightweight container. Basically, the real magic happens in transform. You can declare a module of two linear layers and relu like this. Create the two modules, then call them in call. But actually, why do you need models? You can just declare a function, and in the function you can declare two linear layers, and the result will be the same. You don't really have to use models. I mean, custom models can make your neural network a bit clearer, but you don't have to use them. You can define a neural network as a function. And once again, I already told you, you see how you declare the layers right inside the function. And HK transform works similar to compact of FLAX. And let's write a custom linear layer in Haiku. It's not very difficult, but you have to use get parameter to register parameters and immediately use them. And of course, when network is initialized, the parameter is created, and when you call afterwards, parameter is not recreated but just used. And again, you have name of parameters, shape, type, and initializer. And the magic again happens in Haiku transform. And also Haiku has predefined networks such as MLP with given number of layers and number of features per layer and ReLU non-linearity. By default, you can change it, and other networks like MobileNet and ResNet, but unfortunately no pre-trained models currently. We are finished with Haiku, and finally the final chapter, conclusion. Remember, we had a question, can Jax succeed? Can it beat TensorFlow and PyTorch or at least become a serious competitor? I don't know the answer, but now I can see the good and bad things about Jax. The good things. Jax is very TPU friendly. It also has a reasonably good multi-process and multi-device support without any additional libraries. Functional programming makes things a bit cleaner if you are a professional. Well, beginners probably wouldn't agree. And finally, there is a weight of Google corporations behind it, which probably means something. What are the bad things about Jax? The same functional programming which professionals love can be annoying for beginners because you need instead of one object, two objects, state and code. Apart from TPU, very few real advantages over PyTorch or TensorFlow for that matter. Currently, there are few deploy options. The only deploy options is experimental Jax to TensorFlow converter. Against, you cannot live without TensorFlow. And there are relatively fewer existing and pre-trained models compared to, say, PyTorch. But see the repository FLAX models, there are a few. It's still immature version 0 of everything. API could change in the future, like the FLAX got completely rebooted from an end to line. And that's the end of my lecture. Thank you for your attention. Other